the concept of functions has been studied by mathematicians for centuries. But with the advent of computer science, we realized that we can use machines to compute functions. And then it became very interesting to understand what kinds of functions can be computed easily by machines and what kinds of functions require a lot of computational effort to compute. This is what is meant by the complexity of functions. In this video, I'm going to explain several really interesting results that concern the complexity of Boolean functions. A Boolean function is a function, it's perhaps the simplest class of functions that's interesting. So it's a function that takes a vector whose coordinates are either plus or minus 1 as input and computes a value which is also a number that's either plus 1 or minus 1. Over the last few years, computer scientists have come up with many ways of measuring the complexity of Boolean functions. And in this video, I'll discuss 4 of them, these 4. Now, one of these measures, the degree of the function, is very old. It was studied by mathematicians for a long time. The other 3 are relatively new. But surprisingly, what I'm going to show you is, at least morally, is that all of these concepts, even though they seem quite different at first sight, are more or less the same. Okay, if any one of these measures of complexity is small, then all the others are small too. Okay. Now, in this video, I'm going to use a style that I often use with graduate students, which is that I will not explain all the details of the arguments that I'm going to present. Instead, I'll go pretty fast, just giving the key high-level ideas and drawing the most important pictures that you need to understand the concepts that I'm going to explain. And I'll leave it to you to fill in the details. And in fact, the best way to understand the concepts here is to try to fill in the details and work them out for yourself. Okay. So when you are watching, if at any point something seems unclear or too fast, I encourage you to pause the video and take some time and really try to work out the details for yourself. So what I will do is start by introducing these 4 concepts, and then I'll start explaining several nice results that relate the concepts to each other. Okay, let's start with the decision trees. So a decision tree is a particular way to compute a function, compute a Boolean function. So here's an example of a decision tree. It's this picture here. So it's a tree where every internal vertex is associated with one of the coordinates in the input to the function, and every leaf has a potential output of the function. Okay. And to use this tree to compute the function, you proceed as follows. You start at the root and read the coordinate that corresponds to the root. So in this case, the root reads the coordinate a, so the value of a in the input here is minus 1. So then, if the value is minus 1, you move to the left. Okay, so now move to this coordinate, this node in the tree, and it's labeled by C, and you read that value in the input. If the value is 1, you move to the right. So in this way, the input defines, specifies a path to take in the decision tree, and this path eventually leads to a leaf, and the leaf tells you how to output the value of the function. Okay, so this decision tree computes a particular Boolean function, and the decision tree complexity of any Boolean function is simply the depth of the best decision tree that computes a function, namely the decision tree of smallest depth that computes a function. the depth of the decision tree here corresponds to the number of coordinates that need to be read in the input in order to compute the function. Okay, so the decision tree complexity measures the number of queries that need to be made to the input in order to compute the function. It's a very natural measure of complexity. So that's our first measure of the complexity of computing a Boolean function. The next one we'll discuss is sensitivity. This comes from thinking of the function in a different way. So here's a picture of the Boolean hypercube. Every node here corresponds to an input to the function. So this node corresponds to the all ones input, and this node corresponds to the all -1 input. And two inputs are connected if they disagree in only one coordinate. So these two inputs disagree in only one coordinate, and that's why they're connected by an edge. Okay. So this is a graph that's defined by the space of inputs. And any Boolean function then corresponds to a coloring of the nodes in this picture. Okay. So this is the function that maps this input to -1 and this input to 1. Okay. So Boolean function corresponds to a coloring. The sensitivity of a particular input is the number of adjacent inputs that have a different value under the function. Okay. So for example, in this input has these neighbors, and two of them have a different value, so the sensitivity of this function is 2. Okay. The sensitivity of this input is 2. The sensitivity of the function is just the maximum sensitivity of all the inputs, over all choices for the inputs. Okay. All right, so that's the sensitivity. The next measure I want to talk about is the certificate complexity. It's another very natural measure of the complexity. Now, given an input to the function, like this one, a certificate for this input is a set of coordinates such that once you fix those coordinates, you determine the value of the function. So for example, if this set of coordinates here is a certificate for the function, it means that if you change the other coordinates while keeping these coordinates fixed, then the value of the function does not change. The value of the function does not change. Okay. So that's a valid certificate for this input. And the certificate complexity of the function is the smallest number such that every input has a certificate whose size is that number. Okay. So it's the smallest number such that for every input you can fix that number of coordinates and determine the value of the function. Okay. So that's the certificate complexity. And finally, the fourth measure that we're going to talk about is a very old measure, the degree of the function. This comes from thinking of the function as a polynomial. In fact, every function that takes inputs from plus minus 1 to the n and maps them to a real number can be thought of as a polynomial. And you can just show that explicitly. You know, for every z here, you can define this function, which is a polynomial. And I'll leave it to you to verify that then you have this equality, that the value of the function f can be expressed as a linear combination of these fzx's. Okay, that's something you can verify for yourself. So this shows that every function like this can be expressed as a polynomial. And in fact, when the inputs come from when the coordinates and the inputs are either +1 or -1, the polynomials have a particularly nice structure because it never makes sense to square a variable, right? If you have a polynomial and you have x1 squared, for example, then because x1 is either plus or -1, x1 squared is always equal to 1. So you can just replace x1 squared with 1, and you obtain a new polynomial that's even simpler and computes the function. Okay, so it's no loss of generality to assume that in the polynomial, all of the variables have degree either 1 or 0. And the degree of the polynomial, all right, I should say f here. The degree of f is just the degree of this polynomial. Okay. All right, so I've now defined 4 different ways of measuring the complexity of Boolean functions. And these are all related to each other. And here are sort of 4 different results you can prove that are relatively easy relating these measures to each other. And I'm not going to prove these 4 results. I'm going to leave them to you. The first 2 are somewhat straightforward, so I won't say anything about them. You can try to prove them for yourself. The third one is a little bit tricky, and for that I'll give you a hint, which is you can try to prove it by induction on the decision tree depth of f. Okay. You're trying to show for the third one that given a decision tree, you can construct a polynomial whose degree is bounded by the depth of the decision tree. And for the fourth one is probably the trickiest of these 4. I'll give you another hint, which is that, to prove the fourth one, you're trying to show that if the certificate complexity of f is small, then you can construct a decision tree whose depth is small. And to do this, the hint is that if f of x is not the same as f of y, then the certificates for x and the certificates for y must intersect. Okay, this is an observation that you can prove. And that means that if you query all of the coordinates to the certificate for x, then you actually are querying at least one coordinate from the certificates for many, many other inputs. All the inputs that have a different value from x. So that's a hint. So try to use that hint to prove this bound. So those are 4 somewhat easier results about the relationships of these measures. And these 4 still leave the possibility that the degree can be much larger than the sensitivity. For example, there are several possibilities that are left open here if you think about the relationships we have so far. But now I'll add 2 more bounds. And these 2 bounds are difficult to prove. I would say they involve deeper concepts from mathematics. And these are the ones I'm going to focus on in the rest of the video. So for these ones, I'll give you more details and show the high-level ideas. The first one says that the degree of the function is bounded by the square of the sensitivity. And to prove this, we'll use several facts pertaining to the spectrum of symmetric real matrices. The second one says that the certificate complexity can be bounded by the degree and the sensitivity, and this uses a really beautiful result called Markov's theorem that bounds the derivative of bounded polynomials. Now, I've made another video explaining the proof of Markov's theorem, so if you haven't heard it and you're interested, you can look for it on my channel. So these are the two results that I'll give details for. And let's start with the first one. So here's the bound that I want to prove. I want to show that the degree can be bounded by the sensitivity of f squared. All right, so to prove this result, we're now thinking of f expressed as a polynomial. I explained already that it doesn't ever make sense to square a variable in the polynomial because the square of every variable is equal to 1. So the polynomial for f looks like this. It has an expression that looks like this. The first observation I want to make is that to prove this result, we might as well assume that the degree of the polynomial is equal to n. It's equal to n. And that's because if it's not equal to n, if, for example, the largest monomial is x1 times x2 times x3, if f of x is equal to x1 times x2 times x3 to x to the d plus some other stuff, and d is the degree, then we can just fix all the variables except for the first d variables to arbitrary values. Just fix them all to 1. When we do this, the degree of f does not go down. It remains the same. The sensitivity could go down. But after we do this, we obtain a new function g of x, and then the degree of that new function is equal to the number of free variables. And if you prove this bound for that new function, you also prove it for the old function. Okay. So it's no loss of generality to assume that the degree of the function is full. It's equal to the number of variables. So let's assume that. And once we're given that, what we're trying to show is captured by this picture. We're trying to show that there is some input whose sensitivity is at least square root n. That is the thing that we're trying to prove. Okay, there's some input here whose sensitivity is at least square root n. So that's what we're going to prove, and here's how we'll do it. We'll do it in 2 steps. In the first step, we're going to find a subset S of all the inputs whose size is at least 2 to the n over 2. So the number of inputs here is 2 to the n. We'll find a set S that contains a majority of the inputs, or more than a majority of the inputs, or more than half the inputs, with the property that every pair of inputs in S is a sensitive pair. That's the first step. And then in the second step, we'll use this set S and the spectral analysis of a particular matrix in order to prove, to find an input that looks like this. So let me start by proving. Let me start by doing step 1. So recall that we assume that the degree of f is full, and that means the top coefficient here, the coefficient that corresponds to the largest monomial, is non-zero, and this coefficient you can express like this. You can express this coefficient like this. That's because if you replace for f of x here this expression, then what's going to happen? The very top coefficient here, this one, will contribute itself, because when you multiply with this, the product of all the variables, everything in the top coefficient, all the variables will get squared, and they'll become equal to 1. Okay, so this expectation is over all inputs x that come from plus or minus 1. Okay, it's over a random plus or minus 1 input. Every other coefficient contributes 0, because for every other coefficient, when you multiply this with that, you will get a variable that is not squared. And the expectation of such a variable is always 0. Okay, so you have this identity. And now, suppose, for example, that this quantity, that the top coefficient is positive. It means that the majority of the time, what's written inside here, well, what's written inside here is either plus 1 or minus 1 for every value of x, for every input x. And if this is positive, that means there must be more plus 1 values than minus 1 values. So let's set S to be the set of inputs x such that f of x times this product is equal to 1. And this set S must be more than half of all the inputs, because the value of this coefficient is positive. On the other hand, I claim that every pair inside S is sensitive, and that's because, if you have two adjacent inputs, x and y, and f of x times the product of the xi's is equal to f of y times the product yi's, if these two are 1, then you see the product of xi and the product of the yi's cannot be equal. They must have opposite signs, because x and y are adjacent. But that means that f of x and f of y must have opposite signs for this equality to hold. Okay. So this shows that every pair x and y that are adjacent must be sensitive. They must take opposite values for f if x and y both come from the set S. So this establishes step 1. Now to complete the proof, we now will use the set S and find an input inside the set that has many sensitive neighbors. And the way we would do that is by analyzing this matrix. Okay, and this is sort of the key idea of the proof. Consider the matrix A, where the coordinates of A, every row of A corresponds to an input from the cube, and every column also corresponds to an input from the cube. The entries of A are either plus 1, minus 1, or 0, and they're given by this formula. The xyth entry is 0 if x and y are not adjacent, okay, in the hypercube. And if x and y disagree in exactly the jth coordinate, they are adjacent, then the value of that entry is the product of the first j-1 coordinates. This is a matrix. Now this matrix is symmetric. AXY is equal to AYX. And moreover, it's non-zero only when the inputs, when x and y are adjacent to each other. Okay, so that's a nice feature of this matrix. And the key, another key property is concerns the eigenvalues of this matrix A. And this is a very nice property of the, it's guaranteed by the choice of A, which says that basically half of the eigenvalues, the matrix has been set up so that half of the eigenvalues of this matrix are square root n. Okay, another way to state that is that there is a subspace V whose dimension is 2 to the n over 2, half of the possible dimension, such that whenever you have a vector G inside V, then G is an eigenvector with eigenvalues square root n. So A times G is equal to square root n times G. Okay. Now let me use this claim together with the result of step 1 to complete the proof, to show how to achieve the goal. And then we'll return to proving this claim. So here's how we'll continue. Let's define a subspace W which is equal to the set of vectors G. Well, maybe first I'll make an observation. The matrix A here is a 2 to the n by 2 to the n matrix. So you can think of every vector G here as a vector of length 2 to the n, and that vector corresponds to a function mapping an input x to a real number. So now let's consider the subspace of all G such that Gx is equal to 0 if x is not in S. So this is a subspace, and because S is larger than 2 to the n over 2, the dimension of W is also very large. It's larger than 2 to the n over 2. Okay, and that means that the dimension of W plus the dimension of V exceeds 2 to the n, because the claim says that the dimension of V is 2 to the n over 2. And therefore, there is a vector G, a function G, that is in the intersection of W and V. Now we'll complete the proof. I'll show you how to find this input. This input is the input Z. So let's choose Z so that the magnitude of G of Z is maximized. That's how we'll choose this input. And now consider what happens when you look at A times G at the zth coordinate. Okay, the magnitude of A times G at the zth coordinate. On the one hand, this is equal, because G belongs to V, we have this equality, which means that this is equal to square root n times G of Z, the magnitude of G of Z. On the other hand, you can just write out the formula for this. This is the sum over all x G of x times A x Z. Actually, it's the other way around. Let me write it like this: A Z x times G of x Okay, this is just what it means to when you multiply the matrix with G. But since G belongs to W, we have that G of X is 0 whenever X is not an S. So I might as well here take the sum only over those X that belong to S. The other ones contribute nothing. And now I can write this is less than equal to G of Z times the sum for all X in Z, X in S, AZX. Because Z is the input that maximizes magnitude of G of Z. Okay. And now you see that we are done, because this number here, the sum of X in S, AZX, has to be at least square root n. And that means there must be square root n inputs X that are adjacent to Z that are sensitive. Okay, because every pair in S is sensitive. So that completes the proof. The only thing we need to prove is the claim, and this is the key part of the entire argument. And the matrix A has been constructed so it satisfies this claim. So let's do that. So this is the claim we need to prove about the matrix. And to prove this claim, we'll use two basic facts from linear algebra that I will not prove. The first is that for every symmetric matrix A, real valued symmetrics A, there is a basis. Okay, there is a basis of eigenvectors. Namely, there are m orthonormal vectors e1 through em, and m numbers lambda 1 through lambda m, such that for every I, A times EI is equal to lambda I times EI. EI is an eigenvector with eigenvalue lambda I. That's the first fact. And the second fact, which is very basic, that I will not prove, is that the trace of a matrix is equal to the sum of its eigenvalues. Okay. And then the claim here will be completed by observing, it's going to be somewhat straightforward to prove, that the square of the matrix A is just n times identity matrix. But that means that, the trace of the matrix here, by construction, is 0 because all the diagonal entries on the matrix are 0. Okay, so this is 0. On the other hand, because the square of the matrix is n times I, if you look at A squared times EI for any eigenvector of A, that's equal to lambda I squared times EI. But because A squared is equal to n times identity, this has to be equal to n times EI. And that means the square of every eigenvalue has to be n. So you have 2 to the n eigenvalues, their sum is 0, and each of them, the square of each eigenvalue is n. So it must be the case that half of the eigenvalues are square root n and the other half are minus square root n. Okay, so half of the eigenvalues are minus square root n. So if you now take V to be the subspace, which is the span of the eigenvectors whose eigenvalues are square root n, then you obtain that for every g inside the subspace, that g is an eigenvector with eigenvalues square root n. Okay. So it only remains to show this identity, that a squared is equal to n times I. And let's do that. So to do that, we just write down the formula. Let's compute the coordinates of a squared. The xy coordinate of a squared is equal to this expression. And if x is equal to y, so if you look at the diagonal entries on a squared, this is equal to this number. Okay. But now, because the entries in A are 0 unless x and y are adjacent, are distance 1, you see that there are exactly n values of z that contribute to the sum. Namely, the values of z that are adjacent to x. And each of those contribute exactly 1. So this sum is equal to n. Okay, so that establishes that the diagonal entries of a squared are n. And now we just need to prove that the off-diagonal entries are 0. So that's what we'll do next. So to see this, let's consider an off-diagonal entry, right? So we have a squared of the xyth entry, a squared. Okay, and it's equal to this formula that's written here. Now, if you think about it, the only entries xy here that can be non-zero in a squared must be the ones where x and y are at distance 2. Because the only way you can get a contribution here is if z is adjacent to x and z is adjacent to y. This must mean that the distance between x and y is exactly 2. Okay, otherwise one of these two numbers will be 0 for every z. So let's fix an x and y, a particular x and y where the distance between x and y is 2. And let's say, this is x, this is y, and these are the coordinates where x and y disagree from each other. Then there are exactly 2 choices for z that contribute here. The sum is actually equal to axz azy plus axz prime az prime y. There are exactly 2 entries that contribute, and the z that where here z is the input that disagrees from x in this coordinate, and z prime is the input that disagrees from x in this coordinate. These are the only 2 entries that can, 2 inputs that can contribute. Now I want to show you that this expression here must be 0. And that's true because I claim that if you look at the product of these 2 numbers, right, this number is either plus 1 or minus 1, and this one is also plus 1 or minus 1. If I look at the product of the 2 numbers, which is just the product of all 4 of these numbers, I claim that's equal to minus 1. And that's because if you look at this product of all 4 of these numbers, what is axz? Axz is the product of these numbers. Okay, that corresponds to this bar here. Axz prime is the product of all of these numbers, corresponding to this bar. Similarly, ayz prime is the product of these numbers and these numbers, and ayz is the product of these numbers. When you take the product of all of these numbers, what happens? Well, every number here shows up 4 times. 1, 2, 3, 4. So it contributes 1. Every number here shows up twice. So it also contributes 1. The only remaining numbers that show up in the product are this number, and they each show up once. And their product is -1. So the product of all 4 of these entries is -1. Okay, so that means that the off-diagonal entries are all 0. And this is the point. This is the point of this construction. This was chosen so that this happens. Okay, so that completes the proof of the first bound, which uses a very clever matrix and an analysis of the spectrum of that matrix. And now I want to use to prove the second bound. The second bound bounds the certificate complexity of f in terms of its degree and sensitivity. And this bound will use very different ideas. We'll use a clever result, an old and deep result of Markov about the derivatives of polynomials. And as I mentioned, I made a YouTube video that has a discussion of the proof of Markov's theorem that you can look up if you're interested. So let me describe how to prove it. We want to show that there's a small certificate for f as long as the degree of f is small and the sensitivity of f is small. And the way we'll do that is via an algorithm. So what we're trying to do here is show that if the degree of f is small and the sensitivity of f is small, then it has small certificate complexity. And we'll prove this via an algorithm. So I'm going to give you an algorithm that given an input x, it finds a certificate for x. And I'll show that the size of the certificate it finds is always bounded by this number. So let's look at the algorithm. The algorithm works like this. So in every step, we'll find the y that's closest to x, consistent with the certificate we've already found, and yet f of x and f of y disagree. So find the y that disagrees with x under the function f and is closest to x. Once we find such a y, we'll add all the coordinates s where y and x disagree to our certificate that we're constructing. And then we'll just repeat this process until there are no more such y's. That's the algorithm. Now, one thing that should be clear is that when this algorithm stops, okay, in every step we're adding coordinates and building a certificate. When this algorithm stops, it must be because there is no y that can be picked in the first step. And that means that the certificate we ended up with is a valid certificate for x. Okay, so this algorithm always finds a certificate. We just need to argue about the size of the certificate, and we'll do that by proving two bounds. First, we'll show that every time you find a y in this process, the number of coordinates that we add here in the second step is bounded by the sensitivity of f. I'll show that. And then in a second claim that we'll make and prove is that the number of times we repeat this process is bounded by 2 times the square of the degree. And these two claims together imply that the size of the certificate is bounded by this number. Okay, so let's start with the first claim. So let's say we found at some point in the process this input y in the first step here. Okay, and let's say these are the coordinates in the certificate we've already fixed, and these are the coordinates where x and y disagree. Now I want to claim that the number of coordinates here is bounded by the sensitivity of f. And that's because if you consider, let's say you consider the input z, which disagrees with x on these coordinates and agrees with x in the last coordinate. I claim that it must be the case that the value of f at z is equal to the value of f at x. And that's because if the value of f at z was not equal to f at x, then z would be a better choice for y. Z would be closer to x and yet have a different value from x. Okay. So since our algorithm did not pick z and instead picked y, it must be the case that the value of f at z is equal to the value of f at x. But that means that this coordinate is a sensitive coordinate for y. And in the same way, we obtain that every one of these coordinates here, all of these coordinates, must be sensitive for y. And therefore, the number of coordinates where x and y disagree is bounded by the sensitivity of f at y, which can only be less than or equal to the sensitivity of f overall. So that proves the first claim. To prove the second claim, we'll use Markov's theorem. And this is a beautiful result. I've stated it here. Markov's theorem says that if you have a univariate polynomial p in a variable z, and then then the maximum value of the derivative of the polynomial in the interval -1 to 1 can be bounded by the square of the degree times the maximum value that the polynomial takes in the same interval. Okay. It's a classical result. And now I want to show you a consequence of this result. It says that if you have a univariate polynomial q such that q on input t minus 2 all the way up to q to minus t lies in between -1 and 1, and yet q disagrees in, say, the first two inputs by at least 2, then the degree of q must be the square of the degree must be large, must be at least t over 2. Okay. So this is a statement about univariate polynomials. Intuitively, what's going on here is that, this is going to be an easy consequence of Markov's theorem. We'll see how to do it in a second. But the idea is that if you have, a bunch of points like this, they're spaced out, and you have a polynomial q that's bounded, at least in these points, and maybe in between it goes far away, you want to say that such a polynomial also must have large degree. You cannot immediately apply Markov's theorem because we don't have, at least in the statement here, immediate control on the value of q at points that are in between t and the next point, in between these sort of integer points. Nevertheless, it's easy enough to use Markov's theorem to prove the corollary. So let me do that first, and then we'll apply. We'll use the corollary to prove the claim. Okay, so to prove the corollary, let's set p of z equal to q of t times z. Or maybe I should say that think of t as just a positive integer. Okay. So set P of z equal to Q times T of z, Tz. And now let's apply Markov's theorem. So Markov's theorem says that the maximum over z from -1 to 1 of the derivative of P is bounded by the degree of P squared times the maximum magnitude of P in the same interval. But this is equal to the maximum by the chain rule. The derivative of P is equal to T times the derivative of Q. So this is equal to T times the maximum of the derivative of Q. Okay. And on the right hand side, the degree of P is equal to the degree of Q. So here we have the degree of Q squared. The maximum value of P is equal to the maximum value of Q. But now, let's call this quantity here. Let's write D to be the maximum value of the derivative of Q. Then this the maximum value that Q takes is at most one plus D. That's because, you see, Q, it has to be have value between -1 and 1 on these points, t through minus t. The integer points, sort of t, t minus 2, up to minus t. In the intermediate points, if it has to go very far away, it can sort of, in the worst case, start off at 1 and then go very fast with a very high derivative far away and then come back to 1. This is sort of the worst case. But in this case, the farthest it can go is 1 plus d, because the maximum value of the derivative is d. The maximum value of the derivative is d. So all of this implies that the degree of Q squared is at least t times 1 plus d divided by d. Oh, the other way around. D divided by 1 plus d. But that's at least t over 2, because the derivative of d, this maximum derivative, is at least 1. It's at least 1 because right here, in the interval from t to t minus 2, Q changes by 2. So at some point in between those two numbers, the derivative of Q must hit the value 1. Okay, so d is at least 1, and that means this ratio is at least 1/2. So this proves the corollary. So now let's use the corollary to prove the claim that finishes the bound. To do this, let's define now, let's define the function to do this. Let's say that during the execution of this algorithm, let's say it found inputs y1, y2, up to yt, y sub t. And when it found y1, it added the set s1 of coordinates to the certificate, then s2, and so on, s sub t. We need to show that the number t is bounded by 2 times the square of the degree of f. To do this, we're going to apply the corollary here. Let's define a function g on the variables w1 through wt. It's going to be a polynomial, and this polynomial will be equal to f of u, okay, where ui is equal to either xi or it's equal to xi times wj, and it will be equal, actually I'll write it like this, so it'll be equal to xi times wj exactly when I is in S sub j, and I is in the jth set. Okay, and if there's no j such that I is in Sj, then ui will just be equal to xi. Okay, so that's the definition of g. And the feature of g is that if you look at g of the all ones input, that's equal to f of x. Okay, but if you look at g of if you flip any of the inputs to -1, that's equal to minus f of x, because it's actually equal. In this case, it's equal to f of y2. Well, actually not y2. Yes, y2. Right. It's equal to f of y2. Because when you flip this to -1, that corresponds to flipping the coordinates of the second certificate here, the second set here. And that will give you exactly y2. So that's the point of g. And finally, so now we obtained a polynomial g. If you think about it, the degree of g is at most the degree of f. Okay. The degree can only be smaller. So we just substituted the variables w into inputs for f. And now we need to do one more trick, which is we need to symmetrize g. So pick a random permutation pi of the t coordinates and consider the expected value of g of w of pi of 1 up to w of pi of t. In other words, this is a polynomial which, on a particular input w1 to wt, first applies a random permutation to the inputs and then evaluates g. Okay, and spits out the average value of that experiment. This is also a polynomial with the same degree as the degree of g, but now it's symmetric in its variables. And this, because it's a symmetric polynomial, it can be expressed as some polynomial q of w1 plus w2 all the way up to wt. And this is the polynomial q that we'll apply the corollary to. You see, when you plug in 1 through the all ones vector for w1 through wt here, you get g of the all ones vector, which is f of x, no matter what the permutation. When you plug in, when any of the inputs wi are changed from 1 to -1, you get minus f of x. Okay, so the difference between q of t and q of t minus 2 is exactly 2. It's the difference between 1 and -1. If you haven't seen before that every symmetric polynomial can be expressed like this, then this is something you can also prove by yourself. You can prove it by induction on the degree. It's not too hard. It's a standard fact about symmetric polynomials. Okay, so now we're done, because the degree of Q is the same as the degree of G, and applying the consequence of this corollary here, we get that the degree of F squared must be at least T over 2, which is exactly what we were trying to prove. Okay. So intuitively, what we found here is that these inputs y1 through yt allow us to define a polynomial which depends on t variables, and flipping any one variable changes the value of the polynomial. And that corresponds to a univariate polynomial that has a large derivative at a particular point. Okay. And Markov's theorem says that any such polynomial must have large degree. Okay, so that's the proof of the second bound here. There are a lot of complicated ideas, and I went quite fast, but I hope you can fill in the details for yourself and learn some of these beautiful results.